Okay, welcome. This is my solution to the tensor calculus problem of the day that was posted on 7/20. Okay, part A was we have a position vector, which is a function of a coordinate, but the coordinate is also a function of time. So we want to use the multivariable chain rule to derive a tensor equation for velocity. Okay, how do we do that? It's very straightforward. So we say the partial of r with respect to the coordinate times the change in that coordinate with respect to time. So this is the same as that. And what is the derivative of a position vector with respect to a coordinate? Well, that's a basis vector, right? So we have this term and a basis vector. And this is what is the change in a coordinate with respect to time, which is what? It's the change in length, which would just be the component of velocity, the VI component of velocity. Okay, so that's very straightforward. Part B, express the velocity of a particle in polar coordinates. Okay, so here's the expression that we have. And you see there's this a summation index, right? So we only got two coordinates, r and theta. So the first case it's r, second case is theta. That's it. Now, you may see in the textbooks this equation written as r dot. This would be r hat. This would be theta dot. This would be theta hat. Those are unit basis vectors, and we normally don't do that in tensor calculus. I mean, you can if you want, but it's not really normal. Part C, using the derived tensor equation for velocity that we just did, derive a tensor equation for the acceleration of a particle. Okay, this one's fun. All right, so here's what we got for velocity. Now, what is acceleration? Acceleration is the change in velocity with respect to time. So we're going to take the derivative of this product with respect to time. So we use the product rule. First times derivative of the second plus the second times derivative of the first. Now, we're going to break out these terms, the blue one and the red one. All right, let's do the blue one first. So we want to write that as in the multivariable, the chain rule, as the derivative of a basis vector with respect to a coordinate and the derivative of that coordinate with respect to time. So this is the same as that. Now, we know what this is, right? The derivative of a basis vector with respect to a coordinate, well, that's our old friend, the definition of the Christoffel, the symbol. So we have two free indexes here, ij, there they are, ij. This is our summation index. This is our leftover term. Okay? Now let's look at this and do the same thing to it. We can write it as the change in the velocity, the coordinate with respect to a coordinate, the velocity component with respect to a coordinate times the change in the coordinate with respect to time. Okay, so we're going to put this back in there. I'm going to put this back in there, okay? So we get this expression. Now let's factor out this, the dxj dt. And we got this. Now let's do that old trick we always do of change the I. We're going to swap the i's and k's because they're the summation indexes. They're dummy indexes, okay? So we swap them. Now this is starting to look familiar to you, I hope. Now let's factor out a EI and rearrange things. And I hope you recognize what this is. This is the covariant derivative of a contravariant vector component. Boom. So this is a proper tensor equation for acceleration. It works in any coordinate system in any number of dimensions. Okay? Now, even though this looks very sexy, it's not very practical when you're working in a coordinate system. So that's what we want to do next is express this in polar coordinates. So what we're going to do first is expand the covariant derivative, which we had it there, all right? So you always write down the partial of whatever you're taking the derivative of with respect to the coordinate j. You've got a contravariant one index, the tensor, so you need a plus sign, and the summation index always goes low to high, all right? So you're familiar with this by now. Here's this term, and here's our basis vector. Okay, we want to distribute this inside. It looks like this. Now look at this right here and look at this right here. Let's break the blue one out. All right, well, this is actually a chain rule, right? So we can just express this as the partial of VI with respect to t. And what's that right there? Well, that is just a component of velocity, Vj, right? The change in a coordinate length, in other words, with respect to time, is a component of velocity. So we're going to put this and this right back in here and here. And we get this expression. So we have the acceleration is equal to this component times the basis vector. So this component, we're just going to call it AI. Okay? Now, let's expand what this is. Here's AI. Now we want to do in polar coordinates. So we'll do R first. So you look here, I is a free index. Here's an I, here's an I, here's an I. They're all contravariant. So we go through and put in all of our I's. Then this is a double sum, right? So we got to go through all the permutations of R and theta, which is R, 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 theta, theta, R, and theta, theta. Okay? So we do all that. Now we write down our Christoffel symbols, the non-zero ones, obviously. And we see that we don't have that. We don't have that. We don't have that either. But we do have this, R, theta, theta, right there. All right, so we write that down, minus R. We got two of these components left over right there. Okay, now, let's write down what we found the velocity to be. So the VR component of velocity was dr dt. The v theta component of velocity was d theta dt. So here we have a VR. So we just take dr dt and put it in right there. What's that give us? That gives us the second derivative of r with respect to time. And this is just a product, right? So we got d theta dt squared. And here's our Christoffel, the symbol contribution. Okay, now we do the exact same thing to theta. We go through the exact same procedure. We write down our Christoffel symbols. We see which ones work. And you see that it's only this one and this one are both 1 over r contributions, and then we got this product of terms. And these are exactly the same thing, right? So if you flip these, you get the same answer. All right? So here is what we just wrote down above. So the v theta component of this expression is d theta dt. So we put that right back in there. And we put in dr here, dr there, d theta here, the dr dt, dr dt, d theta dt, d theta dt. And we get this. The second derivative of theta with respect to time, we got two of these, right? Here's the product. All right, so we put all of that back together, and it looks like this. So here is the A1 component, and here is the A2 component. And this is the acceleration in polar coordinates. Okay, wasn't that fun? I'll see you later.